Okay, so we're going to talk about models for, we are talking about models for non-premixed combustion. We just saw we have the beta PDF and we need a model for, let's say, all scalars as function of mixture fraction. And we said one of these could be here Buck-Schumann, but then Buck-Schumann, that's infinitely fast chemistry. Is there something we can do better? And that brings us to the FlameNet models. The FlameNet models, the FlameNet equations we had derived already. The idea is that we assume that the chemistry is fast, but not infinitely fast. That's the point. We don't want to say really, we want to formulate this for very slow chemistry. We want to have departures from the infinitely fast chemistry limit, but maybe the departures are not too large. And then here also we can say the flame is now not infinitely thin, which you would get for infinitely fast chemistry. The flame should be still thin compared to the small scales of the turbulence, or the inner layer should be thin compared to the small scales of the turbulence. So that's very similar to the assumptions we made for the thin reaction zones regime for the premixed flames. And then the inner layer of the flame, it still retains its laminar structure, and then we can use these laminar FlameNet equations to describe this flame structure. Now this shows again how these are derived, but we did this already. And so this is the result then. Example I showed you also. And here this is the result then. So these are the FlameNet equations where we actually assumed the Lewis numbers are equal to 1. Here there is a Lewis number. I want you to think of this as being equal to 1. And then the only parameter that appears here is the scalar dissipation rate. And the scalar dissipation rate now, it can be locally, it can be modeled and can be locally evaluated in a flow field if we want to use this as a model, in a code that simulates a turbulent non-premixed combustion case. So, right. So these are the equations, and we can solve these equations, and then we get C here as a function of mixture fraction here, and maybe also the dissipation rate, and then we can use an expression like this to determine all mean quantities everywhere using here the beta function, and right. So this is a model then we have used, for example, to do simulations of unsteady combustion cases, like simulation in a diesel of combustion in a diesel engine. We said earlier in a diesel engine you have the piston goes up and compresses just air, and then when the piston is all the way up, you inject liquid fuel, and that fuel then evaporates and it ignites and so on. And so that's a model that we have developed a long time ago. This was actually my PhD thesis, developing this model for diesel engines. And the way it works, I just show it here because it's nice the way it works. We have a CFD code, and in the CFD code, we have the Navier-Stokes equations, and then also we have mixture fraction equation. And we can solve these if we know the density, right? I mean, if I know the mean density, I can solve the Navier-Stokes equation. So I need the mean density. I'm also interested, maybe I'm not even interested in the temperature, but I'm interested in pollutants also. So, we have the CFD code. The CFD code solves the equations, from n to n plus 1. And then locally, we get quantities like the pressure. We have, is even the background pressure, which changes because the piston goes up and down. And during combustion, also the mean pressure goes up. And then also, I can locally determine, I use a K epsilon model. I have K, I have locally the value of K epsilon, and I have the variance of mixture fraction that gives me also the dissipation rate. So I get these in each cell, and then we take an average, so that's what the hat says, of the stoichiometric dissipation rate over the entire domain, over the entire, inside of the cylinder. That's the kind of a little bit the trick here. And then I have a dissipation rate at time step n+1. Now, you know, I mean, this was solved for n to n+1. Now I can also solve the flamelet equations from n to n+1 because I know the pressure and I know the dissipation rate for that time. And that gives me then the mass fractions at this time step n+1. I know the mean and the variance of the mixture fraction here from the CFD solution, and that gives me the PDF. I have now from the flamelet code these mass fractions, and I can get the mean quantities everywhere. Yeah, here is the mean and the variance, these mean quantities everywhere. And then what we do is we actually solve an equation for the enthalpy, and knowing the enthalpy, knowing the enthalpy everywhere, knowing the mass fractions everywhere, I can determine the temperature from this, and the temperature then gives me the density, and then I can solve the CFD code for the next time step. So this solution always goes back and forth between these two codes, and everything is done online, which is why it is called here interactive. We call this interactive flamelet model because it's solved online. And this shows the flamelet solution then here as function of time. So you see in the beginning, this is mixture fraction, 0 is air, and this here is the fuel. And so the liquid fuel is at lower temperature, the air is at high temperature because it was compressed. And then you see here, you get, at some time, you get here on the order of a millisecond, the temperature slowly starts rising, and then it ignites fully, and then you get ignition also towards the lean side and then towards the rich side. And then we can use this solution here always as function of time. This shows the results, and maybe I don't need to discuss the results here very much. Actually, this shows a few more examples. So this was this model, which was developed a long time ago. And then it shows here examples of this is an engine that until recently we ran in our lab, and we have also extended these models, you know, making them a little more complex for multi-feed, for multiple injections, and so on. So the examples shown here, I just show this because a video. You have injection. Okay, let's see this again. So you have injection of liquid fuel, and then evaporation, and then a second injection, and then you get combustion. And yeah, this shows the scalars here. For example, here CO. So you see how CO proceeds. And then here's the pressure, and you see pressure goes up and down. Here's the injection. And then a little later, you get ignition of this first part of the injection. And then a little later, you get ignition of the second part of the injection. That's why you get these two little humps here. And yeah, so you know, things like this. Okay, so that's an unsteady flamelet model. Now the flamelet model is, so this model, you know, that's available in I think in most commercial codes, you know, can be used as a model for like a diesel engine combustion. But mostly the flamelet model was used or is used in a form that's called a steady flamelet model. That makes for a you know, very nice model that can be often used for non-premixed combustion simulations. And then here again we start with a flamelet equation for temperature and mass fraction, and then we assume the flame structure is in steady state. Okay, so we assume. So what does that mean in steady state? It means what, you know, there are parameters. I mean, this is an equation. This is an time-dependent equation, and it will always try to go to a stationary state, right? I mean, it will always try to go to equilibrium. And it will reach that equilibrium at some point, and then nothing changes anymore, unless you change a parameter, okay? So you change the dissipation rate, or you change the pressure. These are parameters that influence this equation. But let's say we are interested in a stationary turbulent jet flame, okay? You know, it's ambient pressure, so the pressure doesn't change. And the dissipation rate now, that changes all the time. You know, it changes, you know, when you go downstream, it actually is very high close to the nozzle. And because, you know, it reflects the local gradients, they're very high close to the nozzle, and they go strongly downstream. So in the jet, the dissipation rate goes on the center line goes with x to the minus 4, actually. And along stoichiometric mixture, it goes with x to the minus 2, okay? So it strongly decays when you go downstream. And so that changes then here. But still we say the equilibrium is reached fast compared with the changes of the parameter. And then the flame structure is in steady state. So that makes then for a very nice model, because if this is, if the time dependence here is 0, and let's say the pressure is constant, then the dissipation rate, that's the only parameter that influences the solution, right? And then what we do is just we solve these equations for any possible value of dissipation rate, and then we get a solution of temperature, let's say, and mass fraction as function of dissipation rate and mixture fraction, and we can put that in the table. And doing a simulation, you know, we just look up the table, we use then the presumed beta PDF, and so on. The tabulation can be done here in terms of mixture fraction and dissipation rate, but instead of dissipation rate, you know, sometimes we introduce a progress variable like this, and then it's done in terms of mixture fraction and progress variable. What's interesting, you can also, now you have the solution, let's say temperature in terms of mixture fraction and let's say progress variable, let's say. I know also the PDF, the beta PDF, it depends only on the mean and the variance of mixture fraction, okay? So I can actually now do this integration of this integral, y of z times PDF of z, that gives me the mean. I can do that integration for all possible combinations of mean and variance of mixture fraction. And then I get the mean only as function of the mean mixture fraction, the mixture fraction variance, and the dissipation rate, okay? So that gives me a three-dimensional table, and then, you know, in the simulation, I would just, in one cell, I would look at what is the dissipation rate, or the stoichiometric dissipation rate, what's the mean and the variance of the mixture fraction, and I go in my table and look up the mean density, the mean temperature, and, you know, whatever else. So that's the steady flamelet model, and this here, so it's relatively simple and also available in many codes. I mean, the drawback is you need to always generate this flamelet table first, but once that is done, you know, one can do these simulations. This here is an example, a simulation also we did a long time ago. The bluff body stabilized flame. So the white surface here is just a solid body. And then you have air outside, and the little black spot here in the center, that's the fuel nozzle. And so you get a recirculation region here close to the flame. And so this is how, you know, the simulation looks like. And you see this recirculation here. This one also we had in blue and red, and you could see it in 3D. Okay, and then this just compares temperature and CO close to the nozzle and far downstream. Close to the nozzle means in this recirculation zone, and then far downstream. And you see it's very good. And at the time, it was interesting. A lot of people tried to do simulations for this. And most models either predict what happens close to the nozzle or what happens downstream, but not both at the same time. And this, you know, predicts both. Why? Because it was LES, and LES just, you know, is much better capable of describing these more complex flow physics. And what is this? Yeah, and then we also looked at, you know, cases that have local extinction. You know, I said, really, this is not meant for cases where you have local extinction, but then we have extended these models also in a way where this is then possible. You see here, this is the, these are these Sandia jet flames. They're very famous. They're very often used for validation. Here you have, here's oxygen mass fraction, and you have air here on this side, but the fuel also on this side, the fuel also has some oxygen. This is why, you know, you have oxygen on both sides, and actually at stoichiometric it should go to 0, and the reason why it's not 0 is because of local extinction events that you have, which then leave over some of the oxygen, so this is close to the nozzle, And if you go downstream, then you see at some point the oxygen here is fully consumed. Yeah, these are just a few examples for applications of these models. And what I showed you now is just models, for the simplest cases. And there are more complex cases where the simple version of the model is not applicable, but people have come up with ways to deal with these also. The nice thing about a FlameNet model, it is a true multi-scale model. True multi-scale means, it starts really from the local flame structure. It looks at what is the local flame structure, and then it averages over the local flame structures, rather than first averaging, and then you get an equation for mean, and you try to solve the mean, okay? Because, multi-scale model, it can really tell you the difference between local states, I mean, the non-linearity that you get for local states. So, for example, I have a certain local dissipation rate, and, everything burns fine, and then I increase this dissipation rate a little bit, and it extinguishes. That is very hard to describe in a mean sense if you just have a moment equation, but it's much easier to describe with a multi-scale model. Multi-scale model then has the disadvantage that it's sometimes a little hard to formulate, for complex cases. So that's the disadvantage of this model. Okay, so then let's go to the next topic, which is, now we have two, I call this focus topics. One is here on machine learning, and the other one is on hydrogen, as I mentioned. Okay, so let's start with machine learning. And maybe I'll skip over some of these things because they're not so, or maybe a little too much detail. But anyway, so what is... people talk about artificial intelligence, machine learning, data-driven approaches, and so on. It's not all the same. Here you see artificial intelligence is a very wide field, and machine learning is one of these fields where is one subset of this, where we try to learn with experience. And we try to use data for the machine to learn something, and of course more data then typically improves these algorithms. Examples here for machine learning are, so these algorithms, they're often used here for recognition, language processing, and so on. And I mean, people use it for in image recognition, and people use it for here ChatGPT, you all know, of course, for language, which is a language model. So they're very, very smart algorithms, which I have just learned from data. So they're not smart, really, but they just give you, from a certain input, a certain output. But when you talk to ChatGPT, it seems like, Okay, so there are two different kinds of learning here, supervised learning, unsupervised learning. Supervised learning is training with labeled data. It's a little cumbersome. You need to, let's say, here's an example. I want to train a model, a machine learning model, to recognize what kind of spray I have. And I have two different sprays here. This is a spark ignition engine spray, a gasoline direct injection spray, and this is a diesel spray, okay? And of course, if I show it to you, you see the difference, immediately. But, if I wanted to code this up and say, if I wanted to, in a naive way, I want to code this up, it's very difficult to say, to tell someone or tell a model, what the features are. But what I do here is I just take 1,000 images and I show them to the model in the training process, but I always say, this is a gasoline, and this is a diesel spray, and then the model learns this, and at some point I showed this, which comes from a simulation, and now you, of course, see that this is what is this? Diesel or gasoline spray? Diesel spray, okay? So you, of course, see this, but now the machine also knows this. And of course, you could use, more refined things. You could say, I have this pattern, and I have these emissions, okay? And you could try to link the emissions with the pattern, and things like this. And then, but that's kind of a boring thing because, is nothing new. And but then an unsupervised learning is learning without labeled data. So for example, let's say I have these data here, temperature is functional mixture fraction, from a turbulent jet. Here's this from Sandia flame. And then, you do a classification. You have a model that does classification. And that will tell you, I have one class that looks like this, the other class looks like this. It doesn't know what the difference is really. I mean, one is burning, the other one is extinguished. But it can categorize these. And so if we look at supervised learning, then I say supervised learning creates knowledge in a way, or it is knowledge. It creates a model that I can use, but it's straightforward. And the question is, do I learn something from this, or it's just a useful tool? It's definitely a useful tool, but can I learn something from it also? I mean, if I'm interested in science. And then unsupervised learning, of course, that sometimes it learns from nothing, and so that sometimes it can improve also understanding, and so this can be very interesting. But for both of these, the question is, how do I use them, not just to say, I have an input, I want an output, but how do I use them to really learn something about physics? Now, neural networks are, one of the tools that's very often used, and this is how a neural network looks like. You probably all know how neural networks look like. So I go over this quickly. It's also, in a way, it's not very important. The neural network is just a very complex nonlinear function. That's what it is. And it has input parameters and has an output parameter. Inside this neural network, you have these layers. So each one of these is a layer. And the layer always, or let's say, in principle, each layer has neurons. And then each neuron is determined, the value in each neuron is determined from the neurons in the previous layer, in principle. It can be much more complicated, but let's say it's done like this. So the value of this neuron, y, is determined from all the values of, here you see these arrows, the values of all the neurons here in the previous layer. And so x, these are the values in the previous layer. And then each one of these has a weight. And so this multiplied by a weight. There's also something called a bias. And then here is omega. That's just a connection layer. They don't all have to be connected. Very often you hear the term fully connected means you all to all kind of connections. But they don't all have to be connected. You could have only a few of these connected. That's this connection. This is the weight matrix, this connection matrix. And then you sum them. So each arrow then has a value. You sum them all up, and then you get the sum. And now comes the trick. You put the sum through a nonlinear function. The nonlinear function is shown here. So this here is the input of the nonlinear function here, and then the output is here. And you see this here is for example, is a hyperbolic tangent profile. That's something people use, and the most often used function now is the ReLU function, rectified linear unit, which just looks like this. Very simple function. So there's 0, and then it's all 0 here, and it's linear there. So that's, and then there are variants of this ReLU function, but it just creates a nonlinearity. That's what it does. And also these, they just create a nonlinearity. And then so you always compute this, the next layer, next layer, next layer, and at some point you get the output. Okay? So the output could be, what is the probability that this is a diesel spray? Okay? So it doesn't say yes or no. It says just 99, so, 99% is diel spray, 0.1, most likely is gasoline spray. But it could also be other values. So, for example, one thing we do is we take a neural network. I mentioned this. Input parameters are temperature, equivalence ratio, and some things that tell me something about the fuel structure. And the output is the burning velocity, for example. Or these flamelet tables I just mentioned. We use now neural networks to make flamelet tables. Now, is this new? No, it's not new. Okay? So this is a paper that we published here with my former student, Matthias Ime, and here with Alison Marston. Interestingly, I just realized both of them now are professors at Stanford. So doing machine learning early on gets you somewhere somehow. But so this is a paper we published 15 years ago, long time ago. And we're not the only ones who did machine learning, artificial neural networks at the time. So what we did in this paper here is now people, so one question you should ask, I showed you this is how a neural network looks like, but how many layers should I use? How many neurons should I use per layer? What connectivity should I use? And all these are all questions. I mean, the weights, they're determined in the training. That's really what you determine during the training. But what should be the structure of this? And so we developed here an optimization algorithm that optimizes the structure of this, to give you the best performance of the network. So that, of course, now, it's very well known how to do this. Show some results. Maybe I shouldn't show you the results here really, but this is the optimized neural network. It first turned out, for us interesting, for temperature and source term, the structure looks very different. This is then the error for the temperature, and this here for the chemical source term, especially chemical source term. The error is really small, okay? So we thought, oh great, now we can use this in a simulation. We computed the same case I showed you earlier. And you see here, for example, temperature, one is using a flamelet table, or here a flamelet table, and the other one is a very, very fine flamelet table, very accurate, is this blue line, and the ANN is the red line. So it wasn't very accurate. And we analyzed this, we figured out why. It turned out sometimes the chemical source term is really, really small, and then the network says, oh, this is not very important. Okay, but it is sometimes very important. Even very small source terms are sometimes very important. So we couldn't figure out how to make this very accurate. Okay, and so that's why we gave up at the time. We thought it's not very useful. And then, but now, so why is artificial intelligence now, or these neural networks, why do they become more popular? Because now, so many people are interested in this, and companies are interested in this, and develop these toolboxes, and techniques that you can use. So, for example, everything at that time here, Matthias had to code this up, everything manually, right? Now, you just here use these Keras or whatever toolbox, and it's 5 lines and you get your network. It's very, very easy to do this now. But what's even more important is that things like overfitting, or how to get networks with really good accuracy. There's a procedure now where we know exactly how to do this, and there are special tools or special tricks that we didn't know at the time, we didn't have at the time. Which now everyone knows, and so it's much easier here. For example, here these it doesn't say it here, but these dropout layers or regularization, these techniques that we use now, we didn't have these at the time. And then also, of course, now more complex ways have come out. Convolutional networks, generative networks, reinforcement learning, all of this. And people are looking at different techniques and trying to make something out of it. So I'll show you a few examples here of how we use artificial neural networks. The first one here is simple supervised learning. So that's, I call this stupid supervised learning. So the way we do this, or what we want to do, is we have DNS data here, right? And from DNS data, I can determine mean quantities, right? But so what we want to do now is we filter this here with here a smaller filter, here with a larger filter, and then we get filtered fields, and then from the filtered fields, we want to determine, you know, mean quantities that we need for modeling. Okay, so for example, you know, this is let's say this is the mean temperature field. This is the filter temperature field, but I want to know the chemical source term. Okay, so I try to get this from this. So here we have an artificial neural network, and you know, it's a simple, fully connected network. And as I mentioned earlier, we have, well, let's say we have combined different activation functions. But the point here really is this: we use to avoid overfitting. We use these so-called dropout layers. The dropout layer. So overfitting means. Let me first tell you what overfitting means for those who don't know this. So let's say I have data. This is my data as function of some parameter. Okay? And then what I want is I want a network, and the data looks like this. And then I have one point over here. Okay? Like this, right? And so, so if you look at this, you would think, you know, what's a good model here would be something goes like this, right? Let's say. So underfitting means I don't have enough data, I don't do the training all that well, and I get something that looks like this. Okay? So let's say I have more data, then maybe I get something like this. This is what I want. But the problem is if I have, if I have a lot of data, if I have not enough data, if I have, so each of these neurons has a weight, and maybe there's bias, and I need to determine these. And let's say I have only a few data points, but I have 1,000 neurons. Okay, so I have 2,000 unknowns that I need to determine with just a few data points. And then what the network will do, it will be able, because it has so many degrees of freedom, to fit each point separately. Okay? So it will give me a solution like this. And this here is clearly, you know, is not what the data says. The data says it should be something like this. But the network fits now every single data point, including its uncertainties. And so clearly, for the data I've showed the network, the training, it gives me almost exact results. But you can imagine if I go a little bit outside, you know, these data points, then I get really bad solutions. So that's called overfitting. So there are certain ways that you can do to avoid overfitting. And one is here these dropout layers where you say, during the training, there's a certain probability that I don't use this neuron at all. Okay? So then the network has to be able to give you quite good results without this neuron or with the neuron. And so usually what the network does, when it overfits, you know, it has one neuron that's responsible for this data point, and another neuron is responsible for that data point, and so on. And so by eliminating some neurons during the training once in a while, there's not one neuron responsible for one data point, and that leads to better training. And then the other one is here, this regularization. There's another thing here. So if the network wants to assign one neuron to one data point, it typically leads to very large weights for these neurons. And so regularization means the weights can't be, you know, very, very large. There's a regularization that keeps them the same size or penalizes large weights, and that also helps. So these are just two examples for techniques that help to avoid overfitting. There are many others also. So this here is now a model where we use a certain parameter and to get a certain result. And you see, it's kind of okay. I mean, really, what this should give you a 45-degree line. Here would be a perfect model. Here we use different parameters, and we get a very, very good result. Okay, so it doesn't matter what the input-output is. I think here scalar dissipation rate was the output. Here scalar dissipation rate was the scalar dissipation rate was the output. But so this means it's very important. I mean, one thing means it's very important to choose the right parameters as input. Okay, so that's what we call feature extraction. The question is, what are the correct input parameters? And that's in modeling is, of course, always a big issue. This is a technique that we have been using also for a long time, has nothing to do, in a way, with artificial neural networks, is a technique to do feature extraction. We call this the optimal estimator technique. There's something we always use in modeling, where we have data and we try to understand, what parameters should I use for a model. Now, what is modeling? We said this yesterday. Modeling means expressing unknown quantities in terms of the known quantities. Okay, so the known quantities are then the inputs, in a model, and the model should give me, as an output, some other quantity I need to know. And modeling has two steps. The first one is I need to choose the parameters that I use in my model. And the second one is, once I have the parameters, what's the functional form, right? And this is an example here. We said eddy viscosity, so this is a quantity we need to know. And in LES, the subfilter Reynolds stress. And then, this is the eddy viscosity model, where we have an eddy viscosity and the strain tensor. And then the Smagorinsky model says the eddy viscosity is given here from the strain rate or the magnitude of the rate of strain tensor. But so what are the input parameters in this particular case? Are the elements here of the strain tensor. So I have, these are 6 input parameters. And this here, of course, it just comes out of this. It's not independent. So I have 6 input parameters here. And the question is, are these the right input parameters? Instead of the rate of strain, I could also use kinetic energy, or, something else. And so that's the question, what's the best set of parameters for a model? And that's what we want to find out using this optimal estimator technique. So this shows an example. We have a data set. Doesn't matter what the data set is. We're interested here in soot formation. We use a temporal sooting jet flame. And you see some parameters here. But again, it doesn't really matter. So before we look at soot, we look at just temperature. This shows from the DNS, shows the temperature at each point as function of mixer fraction. Okay, so each point just take the temperature and mixer fraction and plot it in this 2-dimensional space. And now we want to say we want to develop a model where we have only one parameter, and that parameter here is mixer fraction. Okay, and then I can think of different ways to do this. The first one. Or let's say I can think of different ways to do this, and then I can assess these by defining a modeling error. And the modeling error here is just the L2 norm between the DNS and the model. Okay, so I can think of different models. I could say your first one is Book-Schumann. We did this before. Book-Schumann looks like this, and then you see, it's not totally wrong. It has the right behavior, but of course quantitatively it's not very good. And if I now evaluate here this model error, I get a mean error of 180 Kelvin. And then second model I can think of is to say I take a flamelet, but only one flamelet with a scalar dissipation rate of 10 per second. Okay, and that's the red line here. And you see this much better. You visually see it's much better. And then again, I can, determine the error, and it's only 50 Kelvin. And then I could ask the question, what's the best possible model that I could determine, given that data, let's say? What, for this set of data, is the best possible model? Okay? That, the question. And so, I mean, it's easy. I have epsilon is here this right-hand side. And, of course, if we want to develop, if we want to know what's the best possible model, it's just a minimization of the error. So you can just evaluate the epsilon by the t model, okay? And set that equal to 0. That gives you a minimum of the error, right? And if you do that, you can, I mean, it's very easy to do this. You can do this for a given value of mixture fraction, and you will see that this is the conditional mean. The conditional mean, for a given value of mixture fraction, that's the minimum error you can have, okay? So, I mean, just take the derivative here of this thing with respect here to t model, and then it will give you exactly the best model with the lowest, and set that equal to 0. The best model with the lowest error is the conditional mean. And if you look at the conditional mean here, it gives you this. Okay, and that's what we call the optimal estimator. The optimal estimator is just a conditional mean, and it's whatever I do, if I have only this one parameter, I mean, here we said the only parameter I have is mixture fraction. If I fix this parameter, that's the minimum error I can have. It cannot get better. I've just shown this. This is the minimum, okay? So then I can look at the, so I said the optimal estimate, so this is the error again. Burke-Schumann, FlameNet optimal estimator. Optimal estimator here has a certain error, and I cannot be smaller than this, okay? That's the error I just get by picking a parameter. So this means the FlameNet model had an error of 50 Kelvin, but 40 of this was just by picking the parameter, and the functional form is only, this little bit. So the, functional form is almost the best I can do with this parameter. And with Schumann here, you see most of the error comes from the functional form. So, so then, I mean, that puts you in a position where you can say, let's just see what are the best parameters. Because I just saw, if I use, no matter what the functional form, I don't even know what the model is. I just say the mixture fraction is my parameter, then this, you cannot get better than 40 Kelvin, okay? So now I can just test different parameters and see what is the best, what's the smallest error I could get with this set of parameters. So here, for example, if I say I have no parameter, I just use a constant temperature. That's my model, okay? This is the optimal estimator. We call this the irreducible error. Once you pick the parameter, you cannot reduce the error any further. So 400, this was if I just have mixture fraction. Let's say I use the velocity, the local velocity. I mean, that's stupid, but let's say I use the local velocity as a parameter. Is almost like, have no parameter at all, right? But if I use the mixture fraction and dissipation rate, then it's, gets better. And I add also the velocity here, it does not get better. So if this is the accuracy I want, I need to use a mixture fraction and dissipation rate. If I'm fine with 40, I don't even need the dissipation rate, right? So I mean, for any, this is a trivial example, but for any model, if you have a data set, for any model you have, you can do this analysis, determine the irreducible error for many different parameter sets, and then see which one is low enough. And so we did this here, maybe I'll skip over this. We did this here for soot. This is the PDF of soot in these little areas here. And so this PDF we want to model, and we describe it with either just the mean, which is the first moment, or the first and the second moment, which then gives you the variance, or the third moment. You see this is a skewed PDF, so you need some skewness. The third moment should be good, fourth, fifth moment, and so on. And so yeah, that's what's shown here. But again, I'll skip over this. The two lessons we learned here, though, is What's interesting is this. I would have thought, naively, I would have thought, if I have a PDF and I have the first moment, the second moment, the third, all the way up to the infinite moment, I can exactly determine the PDF. If I have an infinite number of moments, I can exactly determine the PDF. It's not true. It depends on what moments you have. Okay, interesting. I didn't know this until we ran into this problem here. The second lesson we learned is the optimal estimator is the conditional mean, and evaluating the conditional mean in high dimensions is difficult. So if I, the temperature example earlier, I have only one parameter, is a one-dimensional space. If I have two parameters, it gives me a two-dimensional space, and I need to do the conditional average in 2 dimensions. If I use 3, 4, 5 parameters, then I have a 5-dimensional space. And even if you have a big DNS, it's somewhere said here how many data points we have here. Even though we have millions of points, when we do a binning, we got only 20. This was in 4 dimensions, I think. We get only 20 points, per bin, which means it's not very accurate, and that creates a problem. So we have developed a technique where we use an artificial neural network to represent the conditional mean, and that then was much better. Anyways, so that's one example. And then, so that's one example of a technique, a data-driven technique that we use very often in modeling, especially when we have DNS data. And then here are a few examples for artificial neural networks that we used to in a supervised learning just to predict fuel properties that we're interested in. So, for example, this is a model that takes the structure of a molecule as input, and it predicts the octane number. And why do we do this? Because we want to design new fuels which have particularly high octane numbers. So having a model that predicts from the fuel structure the octane number, we can invert this and give us a molecule that has particularly high octane number. We call this QSPR. QSPR, models quantitative fuel structure property relationship. QSPR. That's in chemistry this is a big thing. People do this in other fields all the time. So that's simple. I have a database that has the RON, research octane number, motor octane number, and I define what I have to do is I need to define a way to represent the fuel. We use the so-called structural group method here, the Joback groups, where I have a molecule like this, and I just say this is a primary carbon, this is a secondary carbon, and then this is a tertiary carbon, and that's it. And then and you have carbons which are in a ring, you define structural groups, and then, we just say, this is how the molecule is made up. Now the big problem, so I can just use these as input parameters. I have the RON and MON. I can train a network, that's it. The big problem here is compared to Google, we are always data deprived. In here for these combustion properties, you might have only 5 fuels where you know the value or 100, but that's usually not enough to do easy training. So the big problem that we have, compared with other data-driven approaches, areas, is that we usually have not enough data. Okay, so that here, so you see, this is what we have. We have 144 data points, not very much, right? And so what we do then is we use a technique here, which is called k-fold cross-validation. That's what we use in training. Now, the first thing you need to do when you train a network is I have 144 data points. I would usually not use all these 144 data points to train the network, because then I don't know if the result is any good. It might be totally overfitting the data or not. So what we usually do is we define a training set and a validation set. So I take my whole data and I take maybe 70% for training, and when I'm done, I use the remaining 30%, you know, to see if the model is good or not. And that but if I have only 144 data points, that's difficult, right? And so we use a technique that's called k-fold cross-validation, where we say I take my whole data set and I divide it up into k individual batches, and then I do so I have, let's say, 10 batches of data. Each one now has 14 data points, and now I take the first batch out and I train with the 9 remaining, and I see what the error is. And then I take the second batch out and test with the remaining, and so on. So I do this k times, and that gives me an idea then for how to. So we use then the training and the accuracy. We use this, the accuracy we get from this. We use this to decide on how the structure of the network should look like, and also what are the input parameters that we want to use. So this just gives a little bit of information about the network that we use, but that's not really very important. These are the groups that we have defined. So it's, what is this, like 15 different ones. And then we can do the training, and then, well, maybe that's all too much detail, but this is how we do the training. The first question, so we have 15 different parameters as input, but it turns out they're not really all independent, okay? So some of them might be dependent on each other, and if 2 parameters that you use as input depend on each other, that's a problem in terms, again, of overfitting. And so what we do is this. We just pick one parameter out of the 15, and then we train the network with that, and we see what the error is. And we do that for all the 15 parameters, and then we look at what is the best one of these. The best one here in this case was the longest saturated carbon chain length. There's just a number describing the molecule. And then we take this, okay? That's our first parameter, is fixed. And then now we test this first parameter with a second parameter, and again for each single one. And then, the second one here is called the branching descriptor. And then, we go up like this and decide on more and more parameters. And what's interesting is here, this is the octane sensitivity, octane number, and you see the first one's actually the same, but second parameter, the second best parameter, is already different between the two. So each even though they're very, very strongly related, these two quantities, you need different model. You could also say, rather than building up from 1 parameter, 2 parameters, and so on, you could also say, let's just take all parameters and see what I get, and then take 1 parameter out, okay? What happens then? You would think if I take 1 parameter out, the model should get worse, right? But the opposite is the case, okay? That's shown here. So let's start here with 17 parameters, and I get a certain uncertainty. And now I take 1 parameter out, and the model, this is the predictivity, so the higher this value, the better, okay? So I get it here in 0.9, whatever. So I take 1 parameter out, and the model gets more accurate. What happened? If I have too many parameters, I go overfitting again, okay? And so overfitting, again, means as soon as I want to predict something that was not in my training data set, it gets worse. I get a bad result. And so you see, I take 2 parameters out, 3 and 4 parameters out, and it gets better and better. And only then, at some point, it gets worse again. And so we pick a point here that has the highest predictivity. These are the features then we use. And then finally here we use 15 features. So it was more in the beginning than 15. we take 15 features, and then there's a prediction, this is the measured value, and you see it's not all that bad. By the way, once we decided on exactly how to do all these things, how long we need to train, how the structure of the networks is, then once we take all the data, and just train the network once, okay? Because the uncertainty was determined beforehand by the k-fold cross-validation. Okay, so that is one. Here's a second example, and that second example is now for the burning velocity, and that's very similar. Only there's one other interesting aspect here, and I just want to tell you this one other interesting aspect. Here also we use the no, there are two aspects here which are interesting. The first one is, let me see where this comes. So again, we do structural group here. We use similar structural groups, and this shows this here for anisole, how the structural groups look like. And then we define a network, and it is a relatively simple network. And then here's the problem. We have data. We have a lot of data for burning velocities. So we collected all the data for burning velocities, and now this graph here shows how many data points we have at what condition, okay? So this pressure and temperature. And you see we have a lot of stuff for 1 bar and basically nothing for high pressure, okay? So virtually no data here for high pressure. And what we do then is we take some mechanisms, here just a chemical mechanism for fuels that where we think the mechanism is very good, where we actually have some high pressure data, and we validated the mechanism. And then we compute here 3,400 data points for different temperature, pressure, equivalence ratio just for these two fuels. And that then brings in the training data, it provides you with the pressure and temperature dependence that the individual functional groups should have. That's trick number one. So we combine experiment and simulation. And the second issue is this. Maybe this is all too complicated. I just put these up and say it in words. So now let's say I have data for different fuels, okay, and different equivalence ratio. Now the question is, how do I split up my training data and validation data? The first approach could be to just from this database, to just randomly pick points, And that's in fact what the student did, just randomly pick points and then train the model and, So the problem now is the training has seen not all the points, only 70% of the points, but it has seen all pressures at some point. It has seen all fuels at some point and all temperatures at some point, which means, okay, that the validation data, the validation might look pretty good. But if I want to apply this now, either to a pressure I haven't seen, or temperature I haven't seen, or even a fuel I've never seen, it might be totally wrong, because it was never trained to predict a fuel where it hasn't seen at least a few data points, okay? So we do different trainings here. One is, just everything random, and then one where we also do the k-fold cross-validation, but the data we take out is not random. We leave out a complete temperature and pressure, okay? All the data for this pressure is taken out. And then we do a third one where we leave out a fuel, okay? So we have 10 different fuels, and in the training, we leave one fuel completely out, and then we use that fuel for the validation. So that then tests, can the network predict a fuel that's outside of the network? So, right, so if we do that then, this is, all the result for everything random. This is for leave out pressure temperatures. And then this is leave out an entire fuel. And here then you see, if then, you use this for a different fuel the network has never seen, then, I mean, it's still not so bad, but then you do get larger errors, okay? So, but what's nice now about this, I think I mentioned this before, we can now do sensitivity analysis, okay? So, you know, we have, fuels are made up of these groups here, methyl group, CH2 group, you have double bond stuff and OH, ether group and so on. And I can always say now, I just leave one out, okay? I take an artificial molecule and I leave out one of these groups, and then this shows me, you know, what the sensitivity is. So what's very interesting, I want high burning velocity. Ether and alcohol groups, they're really, really good. And what the other thing that's interesting is, if I have an ether group, that gives me a super high burning velocity. But if the ether group is in a ring, actually it's not shown here as newer studies, the opposite happens. So it's not easy and very intuitive to predict all of this. Okay, so I need to, this plot I've shown you already, so I'll skip over this, and is exactly 4:15 now. So we will meet exactly sharp at 4:30.